Wait,
like,
I think I've been there before.
no. It's like it's something you.
I was in the Korean something. I think I heard it.
Like you have a pot in the middle, and then you put like raw meat in it, and then you cook it as it.
Yeah.
And then you. So yeah.
Alrighty,
Just
so
like
let's
that.
go ahead
It's
and
like
get
200
started with this
points.
class. I finished grading the entire exam, but I forgot to bring back the actual paperwork. So I will staple and bring it back on Thursday, but it is fully graded. I was about to offer, for those people who are really anxious, I can send you the PDF version, but then I decided to retract that offer. Because what if all 30 people said, send me the PDF? I don't want to do that. So I will bring it back on Thursday, so that you guys can have your exam back. But the grade is already in Moodle. I have not really looked at the final grade yet. So I will take a look as soon as I possibly can, to look at how the grades are distributed in the class. But you can go to your own grade book and see your own grade and also your ranking in class, okay? Which I think is actually a little bit more important than your actual grade, okay? Because your ranking is kind of what really matters sometimes. Unfortunately, that's what it matters sometimes. I don't have a problem with the whole class getting perfect scores, okay? So the person who's getting 99% is going to be ranked last in the entire class. I don't have a problem with that. But in the absence of that condition, sometimes I would use the ranking to help me decide how to tweak the grades a little bit. Okay. All right. Any other questions before we start today's class? No questions. All right. So in the exam, what was the most difficult question?
Oh yeah, that's true. All of them.
All of them? Well, okay, that doesn't answer the question. Which one is the most difficult?
I thought number 2.
They may be all difficult. The multiplication one? The multiplication one, I think, I have to look at the scores, but I think some people actually did fairly well with that one. I think the second question, is that the second question?
Yeah.
Mm-hmm.
Okay. So the second question was the one that had the average is the lowest of the 4 questions. The floating point number question, most people did actually fairly well with that question, because it's kind of like step by step, and as long as people remember what I talked about in class, in my examples, most people did fairly well with that one. A few people forgot about certain things, but I only deduct partial credit for those things. All right, so getting back to where we left off last time, we were already in this particular topic, which is assembly language programming. You can see the number of hours on this topic is 11 hours. So this is one big topic. It needs to be broken up, at some point into smaller ones. At this point, we are mostly talking about addressing modes and memory allocation. But the way I'm teaching this class at this point is a little bit different from how I taught this class before. Because when we talk about these operands, I want to remind you of, okay, in terms of the toy architecture, what does it mean when we are dealing with an immediate operand? What are we actually doing when we have a register operand? Okay, so those two they were what we talked about on last Thursday. What we'll do today is to introduce a bigger topic, which is memory. Okay, so memory operands obviously are operands that basically refer to content of memory locations. Okay, so let's take a look at this one because there are a lot of the key sentence here is the 386 instruction set offers many different ways to compute the address of the memory location to access. But the bottom line is with any memory operand, the actual content that we are processing, that we're dealing with, comes from a memory location. And that memory location is not a part of the instruction itself. Okay? What do we call that operand when the content that we're dealing with is actually a part of the instruction? Is there a name to that type of operand? What is it? Immediate, exactly. Okay, so the immediate operand is the bit pattern that is a part of the instruction itself. A memory operand is not a part of the instruction itself. Okay, it is the content of a memory location that is not a part of the instruction. Are we doing okay so far with memory operand? Okay, just the concept. Okay. So when we go up back to the previous level, then we start to talk about other assembly language constructs. Now, before we go ahead and do this, we'll go ahead and take a look at the syntax of certain types of operands. So we'll go ahead and take a look at, I'll just call this operands.lowercase s, and we'll go ahead and write a simple program like this one, okay, global_start, which means, okay, so this is a quick quiz, there won't be any points in it. What is the purpose of this line, .global_start? What does it do?
It's a label
Underscore start is a label, but what are we doing with that label?
or exports.
Exports, exactly, very good. So this line exports the label _start to the linker. Because if I don't have this line here, any label defined within a source file in assembly language, none of the labels defined will be exported. In other words, the linker doesn't get to see any label definition in this file unless I specify .global and then whatever label name it is. You can have as many .global lines as you want, as you need, okay? But in this case, _start is very significant because it is the marker of the entry point of the entire program. The linker looks for _start to understand, oh, this entire program starts here. That's the label, okay? .text is kind of important because when you write a program in assembly language, you have basically two binders, okay? One binder is the instruction binder, the other binder is quote-unquote the data binder. In other words, one binder contains all the instructions, basically your C code, if you will. The other binder includes, basically defines all the static variables. So all your quote-unquote global variables, that's in the other binder. The way you switch the binder is to use .text versus .data. When you specify .text, you're basically saying what follows, okay, is going to be in the instruction binder. When you specify .data, you're saying what follows is in the data binder. Are we kind of doing okay so far with that concept that you have two binders? Okay. Now the concept of having two binders is also present in C and C++ programming, except it is mostly hidden from your view. When you declare a global variable, it is in the .data binder. When you continue to write code, like in a subroutine, it is in a .text binder. But C++ does not require you to specifically say, oh, this is going to be in the instruction binder, or this is going to be in the data binder. So for the time being, we're going to use just the text binder, which is the instruction binder. Then we define a label, okay? So the way you define a label is to name the label first, followed by a single colon, okay? This is also how you define a label in C and C++. And then you can start to write the code, okay? So we'll go ahead and start with something that we already know. Well, sort of. So I'm gonna do something like this, and I'm going to make a mistake intentionally, like that, okay? And this one single instruction is already exercising the two types of operands that we have talked about. ABCD is in hexadecimal, we know that because of the 0x prefix, but it also has a $ in front of the entire expression. What kind of operand is that? Immediate. It's an immediate operand. And what about the second operand? It starts with a %. It's a register. Yeah, it's a register. Okay, it's a register operand. Okay. Can someone remind me what is EAX? What is the width of EAX? It's 32-bit. Okay. What about the W next to MOV? What does that? What does that say? It's word. Okay. It's move word, and one word has how many bits? Let me show you where to find that information. Move instruction, and we're looking into the W. I guess I didn't say it here. Okay. I thought it was there. Not. Okay. So a word is 16-bit wide. Okay. A W is 16-bit wide. A B is a byte, and how wide is a byte? A bit. Word is 16, and the L, which is long, is 32 bit. Okay. So getting back to the program that I'm writing here, do you guys see a problem with the instruction? Not the one that I'm writing, but the one that I have written, the line before. Is there a problem?
Yeah.
What is the problem?
So you have 16-bit, but then you store it into 32-bit.
So there's a contradiction somewhere within the instruction, because the what do we say? What is MOVW? Is it an operand, or what is it? How do we call that part of an instruction? It's called the pronunciation starts with an N, but the spelling starts with an N. Mnemonic, very good, okay? That's the mnemonic of the instruction. It makes it easy for us to remember. So instead of remembering the bit pattern of the instruction, now we can just say, oh, it's a move word instruction. But word inside the source code of an assembly language program means it's 16-bit. But when you look at the second operand, it is %EAX, and EAX is a 32-bit register. So we have contradiction within the instruction itself. I'm not going to fix it because I want to show you what, which tool will catch it, and when it is caught, how will this error be represented. So I want to leave it alone just like that. Okay, so let's go ahead and move on to the next instruction. And the next instruction is this, okay? And we'll put it into EBX. There we go. All right. So with the second instruction, you can see the $sign is not there anymore. Okay. Without the $sign, it is not a syntax error. It just means something that is different from an immediate operand. Okay, which is something that I'm going to illustrate at this point. And the rest of the program is just the exit code. It doesn't really matter because I'm not going to trace the program up to that point. But I will put it here anyway, just so that we understand. Oh, okay. To make this process terminate, this is what we need to do. You guys have any questions? Any questions for me?
We're good.
You good? Okay. All right, so let's go ahead and assemble the program first, okay, and see if the assembler is the one that is catching this mistake, okay? So in fact, what I'm going to do is I'm going to introduce yet another error here, okay? So 0x is the prefix of a hexadecimal number. So what if I were to remove the prefix? Okay, this is an intentional mistake once again, just so that we can find out what's going to happen, okay? All right, so we'll go ahead and save the program again, and this time we'll assemble first, okay, G steps to include the debug information. The output, which is the object file, is operands.o, and then the source code itself is operands.s, like so. And we got one error, and it's just a warning too. So on line 4, which is the line where we had a move W instruction, but we have a EAX operand, it's just a warning. But the warning says the assembler is making a decision for us, okay? So what takes precedence? Is it the width implied by the operand, by the mnemonic, or is it the width of the operand itself? Which one has priority over the other one? The mnemonic, exactly. This is telling you if the mnemonic says it's a move word, we will force everything else to be 16-bit wide. So it's basically saying even though I asked for EAX, it's changing EAX to AX. What is the difference? What is AX to EAX? It's the least significant 16-bit. Okay, so AX is simply a different name for the least significant 16-bit of EAX. It's a portion of it. Okay, it's a sub-portion of EAX. Okay. Oh, what about the ABCD problem? Is it complained here? No. Okay. Why not? Let's go back to the source code because I want to tell you why the assembler is not complaining. The assembler look at ABCD and it understands this is not in hexadecimal, so we are not talking about ABCD as a hexadecimal number. Well, if it's not a hexadecimal number, it is just a symbol. What the assembler is thinking is, oh, you're referring to a label called ABCD. Okay? But there's no label ABCD defined anywhere within the source code. How come the assembler is not complaining? The assembler is saying, well, it's a label that is not defined in this particular file. Maybe another object file has this label defined. Whose job is it to cross-reference label definitions across multiple files? The linker, exactly. So we haven't run the linker yet. So that's why this problem has not shown up when we just ran the assembler. Is that making any sense? Now in C++ it's different, because in C++, if you want to refer to a global variable or a function that is not defined within the same source file, you will still need to either have an extern for the global variable or have the prototype for a function. Okay? So you cannot get away with not mentioning what you're referring to at all in C++. In assembly language programming, that's completely different. Okay? You can refer to any label you want, and the assembler will simply say, oh, this label is not defined within the source file. Maybe it's defined somewhere else, and just let it go. The linker, on the other hand, is the one that has to cross-reference everything. So if something cannot be cross-referenced, then it will complain. So this is the next step. I'm not going to fix either problem here. I just want to show you the source code again. So this time we run the linker and say, give me an executable called Operands without any extension, using only one single object file, which is operands.o. Press the enter key. Now it complains. Now it complains and say that on line 5 of operands.s, we have an undefined reference to the label ABCD. But that is why this error is only reported at this point, because the assembler did not understand, oh, ABCD is supposed to be a constant, a hexadecimal number. It simply says, oh, it's just a label reference. Maybe somebody else is providing the label. Is that part okay? I'm illustrating this because I think eventually many of us will encounter problems like this. I want to show you the error messages and why the error messages show up with which tool and what it looks like. Because at some point you will see this, okay? So I want you guys to know how to troubleshoot these issues.
How would you fix that problem?
Well, we're going to fix both problems here. The first problem I'll fix by just removing the E here. The second problem, I will just make this a hexadecimal number. Okay, so this will resolve the problems that we had earlier, but there's still one problem. Okay, because I still have not explained on line 5 what is it doing. It's not it's not an immediate operand. What is the first operand if it's not immediate? What is ABCD in hexadecimal really specifying? Okay, so we'll explain that later. Okay, we'll run this in GDB first, run into a brick wall, and then I'll explain what is the splat on the brick wall. Nobody's getting it. Nobody's mapping. Nobody wants to be the splat on the brick wall, I guess. Okay. So okay, it's all virtual. We can run this program again and again. Nobody's gonna die. Okay, so reassemble. Every time we change the source code, remember you have to reassemble first and then relink. Okay, so this time I did not get a single error with either one, so it's time to GDB the program. Now you can certainly run the program all by itself by saying /operands, and it's going to crash. Okay, but that crash is not going to tell you why it crashed or where it crashed. It simply says segmentation fault. So segmentation fault is a very general term that says your program did something it's not supposed to. That's all it's saying. Okay, but which instruction is doing that? We don't know. Well, what type of thing did it do that it's not supposed to do? We don't know either. Okay, so that's why when you have a segmentation fault, it is usually very beneficial to run the program in GDB instead of on its own on the command line. Okay, so now we're in GDB, and what we'll do is we'll basically put a breakpoint on _start, which is the first instruction. Run the program, and then we can single step. So single step the first instruction, and what do you think should be in AX at this point? The bit pattern of ABCD, which is, well, let's take a look. So you can do a print, and remember, every time you want to refer to a register in GDB, you have to do it with a $ before the name, because we don't really have a variable called AX. So as a special name for a register, you have to precede it with a dollar symbol. Okay, it shows me some assigned interpretation of the bit pattern. I don't want to look at it this way. I want to look at this as a hexadecimal number. And that's how we do it. /x forces the interpretation to be, or forces the representation to be in base 16 instead of the default, which is signed decimal. Okay. Are we doing okay so far at this point? Is there anything surprising at this point? Kind of boring, right? Okay. So now let's go ahead and run the instruction on line 5, which is this one here. Okay. So we single step, and we run into a problem. Okay. So we know for sure now the problem is on line 5. It doesn't still quite explain what it is. Okay. Well, let's try to think of reasons why this might fail. Do you think EBX can be the problem? No, cannot be a problem because the registers are always available to an instruction. So it must be the first operand. This first operand is called a direct operand. It's not immediate, okay? It is called a direct operand. What do you think it attempts to do? It attempts to go to location ABCD in base 16, retrieve 32 bits from that location, and then copy those 32 bits into EBX. Am I doing okay so far with that? Okay? So if I were to rewrite this in a different way, in a quote-unquote C language way, this is what it really is trying to do, okay? It's trying to do a set var, okay, set variable. You can't really do this, but I'm just using this as an example, okay? So the expression it's really trying to do is something along this line, okay? Okay, so let's take a look at this expression here. In fact, I'm going to make it slightly better by using an extra pair of parentheses. Okay, so how many people feel that, okay, I think I know exactly what this line of C code is doing? Okay, what is the right-hand side specifying? How is ABCD as a base 16 number used here?
Casting it into a character name.
I cast it into an address of a 32-bit integer, and then what do I do with that address? I dereference it. Exactly. And do you think memory location ABCD is accessible to this process? It's not. Okay. So out of a 4 GB memory space, each process can only access like tiny little bits of that memory space. Okay. And this is not one of the locations this program has access to. How do we know that? Okay. Let's try this. So instead of using set var, which definitely is not going to work, I'm just going to say, tell me what is at that location. Print it instead. Is that okay? Okay. So I'm not changing anything. I'm just saying, tell me what is at that location. Press the Enter key, and it says cannot access memory at address ABCD, which is actually what the first operand of the instruction on line 5 was trying to do. Is that okay?
Why can't it access?
Because, well, that's a very good question, but it has a long answer. Okay. Because I'm using a 32-bit architecture, that means the address bus is 32-bit wide. Okay, so if you go back to the toy architecture, which has a 8-bit address bus, now we have a 32-bit address bus. With a 32-bit address bus, how many locations can I potentially access? About 4 gigabytes. Okay, so about 4 gigabytes is the limit of within this space, which is a huge amount of bytes, right? So when you look at this entire space, that in theory I can address, okay? But out of this entire space, I'm not allocating 4 gigabytes for this program. The operating system is not allocating 4 gigabytes for this program. It's only allocating as much memory space as needed by this program. Is that making any sense? Because you don't want every single program to take up 4 gigabytes of your computer. Because I know some of you gamers out there with, you have what, 32 gigs of RAM or something like that? How many people have 64 gigs of RAM? No one yet, okay? Those days will come. But even with 64 gigs of RAM, okay, if each process is taking about 4 gigs of RAM, you can only run how many processes? 16 processes, okay? And do you think 16 processes is a lot, or is it not quite sufficient to run any practical environment?
It's not that simple.
Well, let's take a look. Because I like to show you these things, just so that we have an understanding of how things are. So there's a command called ps in Linux that shows you, that lists all the processes, okay? What is a process? How does a process relate to a program?
Process is a program.
It's not a program. It is a program in execution.
Yes.
A process is a program in execution. Okay, now it is very important that you understand the concepts at this point, even though it's not specific to this class, okay? A process is a program in execution. What is the difference? Okay, let me give you an analogy, and that will make it very, very clear. A program that is on the hard drive that you have installed is nothing more than a binder that contains the instructions of how to do something, okay? So when you install a program on your hard drive, okay, LibreOffice, okay, WinSCP, and so on and so forth, they are really just entities on your hard drive. They don't do a single thing by themselves. When do they become useful? When you run the program, right? So when you run the program, it is like having a worker to read the operation manual and actually do something. Is that okay? So you can now have multiple workers following the same instruction manual to do something. Is that making any sense? So each worker following the instruction binder of a program is a process. Is that concept okay or not? Okay. So the number of processes that we run in a particular environment is important. It's not the number of programs that we have installed, it is the number of processes, the number of instances of programs running that is actually important. So what I'll do is I'm going to give you an idea of how many processes are actually being run at this point. These are all individual processes, and you can see, well, let me just go through the pages here, okay? This is the number. Okay, let me give you another idea of what we're dealing with here. We have 140 lines of the ps command, which means at this point there are 140 processes running concurrently. If each one takes up 4 gigabytes, it will take up, what, 4 times 140, which is a huge number, okay? It's in about half a terabyte of RAM. It doesn't make any sense, okay? The point is, it doesn't make any sense to allocate exactly 4 gigabytes for each process. So the next question is, so how much are we going to allocate for each process? What do you think makes sense? As little as possible, right? Okay, we'll give each process just the bare minimum amount of resources that it needs to run. The program that we just wrote should not require any resources, right? I did not declare any variables whatsoever. It only contained, what, 6 instructions, 5 instructions or so. So it should not be allocated even close to 1 megabyte, maybe a few kilobytes, that's all. Is that making any sense? All right, well, so let's say that it puts the certain code here. It still has a stack, which is usually about here. The stack itself is a few megabytes large. It's not even close to, like tens or hundreds of megabytes. So we are looking at tiny little portions of RAM that is really being in use. What about the rest of this address space?
Unused, right?
Idle. They're not idle. They're unused. They're simply there, doing nothing, okay? They are mapped to nothing. So that means if I try to access anything other than the 2 little chunks that are really allocated and in use by this process, if I try to access any other locations, it will give me a segmentation fault. Because the operating system combined with the processor will say, hey, this location is not even allocated to this process. You cannot access it. Is that making any sense? Okay, so that's why we ended up with the error that we got when we attempted to run this, when we attempted to get to this location. That is the problem. Okay, are there any questions at this point? Yep.
How do we find the specific memory?
Say again?
How do we find the specific memory?
How do we find the specific memory to?
Yeah, like the specific location. to access it.
Oh, you mean where it is actually allocated?
Yeah.
Yeah. Oh, yeah. Absolutely. In fact, well, we don't see it here, but when we set up the breakpoint, it actually displayed an address. How about that? What do you think is 8048054?
Address of instruction.
The address of the instruction where we set the breakpoint. Do you think that location is accessible to this process?
Yeah.
Do you think the print command would work at this location? Let's give it a try, right? Okay, so we'll go ahead and give this a try. I obviously cannot remember the entire number, so I'm gonna do the copy and paste approach. Okay, so we'll say copy, and then we'll repeat this command and paste it here. Paste, there we go. Press the enter key, it shows us some random number, but remember, we can always print it in hexadecimal, like that. And, oh, you can see ABCD, don't you? You can see ABCD and then B866, right? What, again, what is the operand of the first instruction? The first operand of the first instruction. What kind of operand do we have? It's called an immediate operand, okay? And as an immediate operand, it is a part of the instruction. What are we printing here? The memory content of the instruction itself. Are you surprised to see ABCD as a part of the instruction? No, because that's the way it's supposed to be. So you can see all of these concepts are related. Okay, the demonstration is actually not illustrating just one thing, it's actually reinforcing some of the other things that we have already talked about. Okay. Now, using print and dereferencing is not really the best way to examine memory locations or examine the content of memory locations. Can someone remember from the previous class what is an alternative to look at the content of a memory location? Backtrace is good for stack related stuff, which we are not dealing with just yet. Okay, but I did use that command earlier, well, in the previous class, to show you the opcode of an instruction, the bit pattern of an instruction, because I was showing you the immediate operand is a part of the instruction, and I did use that one command in GDB. Can anyone remember what I used?
Is that the X slash?
The X command, exactly. Okay, so the X command is the other way to do it. So with the X command, you can do a slash, and then you can specify how do you want the content to be printed. Okay, so let's go ahead and look at this as bytes. Okay, so I want to look at these as 4 bytes, and each byte I want to display in hexadecimal. So the 4 stands for 4 things. Okay, what is one thing? It is a byte. That's what the B is. And how do I want to print out that byte in hexadecimal? That's what the X is. Okay, and then you just have to specify the address. You do not need to do the dereference. Okay, do not do the dereference. All you have to do is now to specify the location. Okay, you can specify the location as a label. You can specify the location as a hexadecimal number. You can specify the location as a register, which will come in really handy later on. But any expression that evaluates to an integer is going to be okay. All right. So these are the 4 bytes. Okay, these are the 4 bytes at location, and you can even see underscore start here, because if the location does match any defined label, it will show the label for debugging purposes. And you can also see ABCD as a part of the instruction. ABCD, and they are exchanged or swapped because of what? We've kind of talked about this as well.
Because that's just the way that Intel does it.
Yep, it's called 1, little 2, little 3, little. Indians, not Indians, okay? Okay, we need Mickey to come with a ukulele one of these days, and then we'll play that using a ukulele, okay? Because then you will absolutely remember, okay? It's the Little Endian convention, okay? It stores the least significant byte first, Okay, in this case, we can definitely see that CD, which is the least significant byte of the 16-bit quantity, has the location of what? 54 refers to the 66, 55 refers to B8, so 56 refers to the location of the CD, and then 57 refers to the location of AB. This is the little endian convention, which stores the least significant byte first. And that's why it looks swapped, because we are actually, the location or the address of the CD byte is lower than the location that stores the AB byte. Is that okay? All right? So this is not really just an independent, separated experience to only talk about direct addressing mode. It's also a reinforcement of something that we have learned before. Okay, so hopefully these repetition will help you kind of get used to the GDB tool itself and also the concepts that I'm trying to illustrate in GDB. Are there any questions at this point? Yep, go ahead.
Is each address index, does it belong to a bit or a byte?
That's a very good question. The Intel architecture, like most modern architecture, is what we call byte addressable, which means the address is each address specifies the location of a byte.
Mm-hmm. How do you access separate bits of certain bytes?
You have to rely on bitwise operators.
Okay.
So you have to use bitwise AND to filter out only the bit locations that you are interested in, and then you can use a shift operation to shift it to the right location that you need.
Okay.
But there are no direct way to get to individual bits.
So if you increment it by 1, you will jump to the next byte?
Correct. Yep. In fact, we can demonstrate it here as well, right? Because we can just say, oh, show me just 1 byte. Okay, that's the 66. Give me the next byte is the B8. So every time you display a byte, it is just 8 bits. But that's the smallest unit you can specify using just the address.
Thank you.
Yep, that's a very good question. Because there were architectures in the past where the location of each address is not a byte. It's not a word, it's not a long word. I think the cyber mainframe computer had a word width of 36 bits, which is really odd. Yep.
What if you, in C, you declare a Boolean variable,
Okay.
array and stuff, and you store them in memory locations? Is it going to take up the whole byte to store a Boolean?
Well, that's a very good question. So to answer that question, I know it's a little bit out of the way of this class, but I think it's a very good, valid question. Let's go ahead and design an experiment to find out. Okay? Because this is something that you guys can do also, okay? Because you already have the necessary tools from your previous class to do just that. Okay, so I'm just going to name this program bool size because we want to find out the size of 1 Boolean, right? So we'll go ahead and do this in a few ways. Okay. So the first thing I want to do is to say we have a Boolean array, and we'll say this is array A, and let's give it 16 items here. In fact, we'll give it 32, just to have fun with it. And then we'll have a single variable, which is a bool, just call it a B. And that's the entire program. So obviously this program by itself is not going to tell us anything. But what I'll do is I'll compile this program and run it with GDB. So everything is going to be done in GDB because GDB actually understands a good portion of C++. So let's go ahead and G++-C-G boolean size.cpp. That compiles, okay? And then we'll do a link to bool size.o. GDB, this particular program. We definitely want to set a breakpoint on line 6 because otherwise I would not have a time to stop to examine stuff. So now we are at the breakpoint here. So what I want to do is to print the size of A. Okay, there's an operator. Okay, size of is not a function call. It is called an operator. Okay, it's an operator that is defined in C and C++. It tells you the number of bytes used by whatever is inside the parentheses. Okay, so I can now say, tell me how many bytes A as an array of bool is using. It tells me 32. So your suspicion is right. Okay, it's using up 1 byte per Boolean, which is not the most efficient way of doing things from the storage perspective. But when it comes to the time of computation, it makes sense because you don't have to do the bitwise AND and the shift operation.
Okay.
So it is wasteful in a way, but that's how it's done in C++. Okay. But just to confirm it, we can also look at the size of B, which is a single bool. It is 1 byte. So that's double confirmation. Because I try to define an array because I want to find out whether the compiler would do optimization when it's dealing with an array of Boolean as opposed to one single variable, which is a bool. And the answer is no, the compiler does not do any storage optimization when you have an array of Booleans.
Okay.
So you might as well just say it's a char array. It uses it will allocate the same number of bytes if you were to have an array of 32 chars. Yep.
Thank you.
Yep.
But another question: what if you use the size of the Boolean in a program? Will still return the memory, just like a 32 and a 1.
Yep.
Okay.
It will. Yep. Exactly.
Thank you.
So if you were to use a cout to print it out from inside the program, it would have given you the same number.
Okay. Thank
Yep.
you.
All right. But I just want to illustrate it because there are a lot of questions that we might ask, but many of those questions you can design experiments like what I just did. And by doing that, you're, one, you're confirming your understanding of the concept, and two, you are using the tool a little more and you become more proficient with the tool as well as the concept. So I really encourage you guys to do something like that. Just write a 5-line, 6-line program to find out, oh, okay, I wonder, blah, 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 blah. Well, this is how we get to the answer. You can certainly search for it as well, but this is a way it's really hands-on.
Thank you.
All right, so where were we? Oh, right, the direct operand, okay? All right, so now that we are done with the introduction of the direct operand, let me see if you guys remember the direct operand from one of your homework assignments, actually. Is it the homework assignment or is it the test? I think it is the test. Okay, let me find out. Okay, so we go to apps.lawschools.edu. Nope, that's not work. I'm just going back to the test to see if that was the question in the test itself. There's no grade here, so don't worry. And this is it. Okay, the address register. Yep, this is the direct operand. So when you look at this particular question in exam number 1, we are actually referring to the direct operand. If I were to rewrite this as a, well, it depends on what piece it's pointing to, so it's kind of hard to describe it. But we can see that register B is the source operand, and then whatever location is a part of the instruction, because it's pointed to by PC, the program counter, is the address. So this is the direct operand method of accessing an operand. Is that okay so far? Does everybody kind of understand what he's saying? No? Okay, let's go back to the instructions, okay? Because I really want to show you what it is, okay? And operands.lowercase(s). So this time we want to look at the instruction of the second instruction, okay? Because I want to find out, okay, is ABCD a part of the instruction? Okay, because if it is, then the approach that you use in the exam is going to be helpful here. So let's take a look at in GDB again. This time we're still dealing with operands. Put a breakpoint on line 5, okay, because I just need to know the location. Okay, so now I can do the examine. I'm not sure whether I can do that or not. So let's try that. 0x80488058. Oh, okay, that works. Okay, so I'm displaying the instruction at that location, at the breakpoint, are you guys surprised at all that it's showing me that this is start +4, it's a move instruction, the first operand is ABCD in hexadecimal, the second operand is just DBX. Is that surprising to you?
What's the +4?
Huh?
What's the +4?
The +4 means this is not at the label start. It is 4 bytes after the label _ start, which makes sense, right? Because this is not the first instruction. The first instruction took up 4 bytes. This is the second instruction. It starts at the location of _ start +4. Okay, that's a good question. But other than that, it's not surprising. Okay, so the next thing we want to do is to say, oh, okay, is ABCD a part of the instruction? Okay, and the answer is, let's take a look. So this time I'm going to display the same location, but I do not want to display as an instruction anymore. This time I'll display as 8 individual bytes in hexadecimal. Okay, so there we go. Do you see ABCD in this particular sequence of bytes?
Yeah. Yes.
Yep. And on top of ABCD, we also have 2 extra bytes of zeros. Because the 4 bytes, and then just point out exactly the 4 bytes, the most significant byte, second most significant byte, the second least significant byte, and the least significant byte. So these 4 bytes, which are 32 bits, is the address. It specifies the address where I'm supposed to grab the content, and the content at this location, ABCD, is the actual operand, or at least if the instruction runs, that's what it's supposed to do. So that means with both immediate operand and direct operand, the instruction itself contains the constant in the case of an immediate operand, or the address in the case of a direct operand. It is a part of the instruction. Okay? Anything that is a part of the instruction, how do we get to it inside the toy architecture or any architecture? Which register points to a part of the instruction? Well, let's go back to the question in exam number 1. If you just look at this part of the question, which register do you think which register points to a part of an instruction?
Program count?
The program counter, exactly. Okay, so when you see the reference of PC, it is basically saying, give me a portion of the instruction, and let me do something about it. Okay, so this time, what is it doing to the instruction or the portion of the instruction pointed to by PC? It puts into a register called the address register, and then later on, what do we do with the address register? We dereference it.
Yeah.
And that's exactly how a direct operand works. Yep.
I have a question for the homework assignment. The initial 0 that you draw for the first location of RAM, where do you draw it from? Because I can draw it from pretty much anywhere.
That's correct. You're talking about the current homework assignment, the one that's due
Yeah, I
on
think so.
Thursday?
Yeah.
Yeah, let's take a look at that. So let's see here. That will still be in control structure. I don't want to lose this tab, so I'm going to use another tab for that. So that would be the immediate operand. There we go.
Yes.
Well, it depends on the actual location, because when you have a reset, PC resets all the way back to 0.
Mhm.
So if you really want to test this code, you want to put something other than a 0 into location 0,
Mm-hmm.
and then you can later on check whether register E ends up with that content.
Okay.
Is that okay so far? So to test it, you can just run it the way it is with all zeros, but you wouldn't be able to tell whether you have 0 in register E because that's the default, or whether you actually put a 0 there. So to test whether you actually put the content, you want to change location 0 of RAM to some other content, run the microcode that you specify and see that register E ends up with that value.
Okay.
Okay. All right, so getting back to here, are there any questions? No questions? All right. Well, if there are no questions, we'll go ahead and see if we can use. We can specify, instead of just a random location as a constant, can we refer to something that can actually move something into EBX? What do you think? I mean, how do I know which location is actually used by the program so I can at least, demonstrate, hey, I can move something into EBX and the program runs? Underscore start, exactly. We just demonstrated that, okay? So in this case, we can say underscore start, okay? And you know what? I'm going to change this one too to underscore start because I want to demonstrate or contrast what these two instructions do and how they're different, okay? So when you look at these two instructions other than EAX versus EBX, the most important difference is the $sign, okay? The first one is move immediate, the second one is move direct, okay? It doesn't seem to be very important to you, the $sign, okay? But it actually makes all the difference, okay? So what we want to do is to recompile this program, reassemble, relink, and then run it again. And then you guys should know what should be in EAX and what should be in EBX, okay? So we'll go ahead and do this. AS-G steps for debug information. Operands.o is the output. Operands.s is the input. Link operands is the output. Operands.o is the input. GDB operands. This is the program. Put a breakpoint on line 4 because that's where we're going to stop. Okay. All right. So right away we should know the answer to line 4, because what do you think should end up in EAX? The exact value that should end up in EAX after line 4 executes.
Address of the underscore start,
Which is 80488054.
yeah.
Okay. All right. But from this, how do I know what should be in EBX? Remember the commands that we talked about before? Remember the X command? Okay. We examine what is at that location. So we say, give me 1. And in this case, a W does not mean 16-bit. A W in GDB means 32-bit. If you want to specify 16-bit, it is H for half word. So inside GDB, W has a different meaning. It means 32-bit wide. We want it to display in hexadecimal at the location of 0x80488054. That should be in EBX after line 5 executes. Okay, so let's stop here and make sure that it makes sense. Okay, what I just said makes sense. Are there any questions? 0x80488054 is an address, okay? But that's also what the label is defined to be. It is a label that is defined to a particular address. Is that okay? Mm-hmm. And because on line 4, we have a move immediate instruction, it means whatever the label is, we'll just move the value of the label, not at the label, to EAX. And that turns out to be an address of 80488054. Yep.
Can you repeat that? It sounded like you said move the address at the address. Is that what you said?
No, I said I moved the address that is the value of the label itself. So the label, in C++, a label can only be a location in your code, in a function. But in assembly language programming, a label can be defined to anything. If you want to, you can define a label to be 5, just a value of 5. In this case, underscore start is defined to be, as a label, it is defined to be the address of a location. Move immediate says, whatever the expression is after the $sign, whatever the value of that expression is, just copy that value to EAX. In this case, that value turns out to be the value of just the label, not the content at that label. It is just the label itself. The label itself is defined to be 80488054 in hexadecimal. Okay, that's the move immediate operand or instruction. The second instruction on line 5 is move direct. How is that different from move immediate? It treats the label differently. Okay, the expression underscore start is no longer the pattern, the bit pattern that we are copying to the destination. It simply specifies the address where we'll grab the 32-bit to copy to EBX. Is that okay? Because this is a very important and yet kind of subtle difference. Okay. So what we'll do is we'll now single step both instructions. Single step the first one. Oh, okay, run it first. Single step the first one, print /x $EAX. Okay, not surprising. Single step the second instruction, print /x $EBX, and it ends up to be what it is supposed to be. Because, oh, wait. No. I think I missed something. This is the content at that location, and yet it is different here. Okay. That is what is at that location. Do you guys see a problem here?
Yeah, moves
The least significant byte is changed from B8 to CC. That is not. It's not right. Why would it do that? Okay. Let me show you what I think is a problem. I cannot explain it just yet. When we ran this command to examine what is at location 0x804854, it displayed, it had this content. The instruction move direct is moving exactly what is at that location, which is _start to EBX. So that means EBX should end up with a bit pattern of this. After we perform the instruction of the move instruction and we examine what is in EBX, it showed us that it had this content instead. It showed us that it had the content of 48054CC instead of a B8. So it's off just by a little bit. Okay, it's not off by a whole lot, but it's enough to be different. Okay, and I cannot quite explain that. Let's see. Okay, there's another command to display the content of a register. I don't think it will make any difference. IREBX is the abbreviated form of info register EBX. It will still do the same thing. It will still show us what is in EBX, and it shows us that EBX has a value that ends with CC, so the print command is actually correct. This is really weird. Okay, let's try this then. 804844 /x. And the location has a content that ends with a B8. And yet, when I display, the register of EBX, it has the least significant being CC. Okay, what is CC minus B4? Can you guys do subtraction in hexadecimal?
0.
Okay, let's do this. Okay, a C is the same as a 12. Okay, and so 12 minus 8 is a 4. Okay, and then we have the second digit is C. C minus B is a 1, but that 1 does not mean a 10. It is 16. So we have a 4 from the least significant digit subtraction. We have a 1 from the second least significant subtraction. So we end up with 16 plus 4, which is 20 bytes. So it's 20 bytes off from what I expected the answer, which is kind of really weird. I don't quite. Oh, you know what? I think I know why. Okay, let me just rerun this experiment. I'm not going to tell you exactly what it is. I will rerun the experiment, and you can tell me from the way I rerun the experiment, you can tell me what I'm actually suspecting. So not only are you debugging the program, you're trying to read my mind as well. But I want to lead you guys to figuring out stuff like this, okay? So what I'll do is I'm going to put a no-op instruction here. NOP stands for no-op or no operation. Okay, it doesn't do a single thing. Just doesn't do a single thing. Okay. In fact, I may not even. Well, yeah, I need to do this step. Okay. So we rerun the assemble command and then rerun the linker command. The dollar sign, the exclamation point. The exclamation point is basically telling bash, which is the shell, the command line interface, to rerun the previous command that starts with AS and LD in this case. It's a really handy kind of shortcut. If you use the command line a lot, this is a really neat shortcut. So now we can do GDB again. Okay, so GDB. Oops, I forgot to say GDB what. So GDB operands. I still need to set a breakpoint, but this time I can set a breakpoint on line 4. Okay, so B4 like that. And set up another breakpoint on line 9 right before the move $1 into EAX, because when you stop on the line, it has not executed that line just yet. Okay, and then we run the program. We say, tell me. I forgot one thing. That won't work. Okay, let's do it again. But I think I got it. So we'll set a breakpoint on line 9, okay? Run the program, now it stops on line 9, okay? Then we go back and do what we used to do, okay? So we say, tell me what is the 32-bit thing in hexadecimal at location underscore start. And underscore start is, I forgot to print that. Okay, tell me what is underscore start. Okay, and then we can say, display what is at that location. One thing, 32-bit in hexadecimal at the location 0x8804854, and it has that content. Okay, it's changed this time because we have a no-op instruction. Okay, so now we'll go ahead and check again. So tell me what is in EAX. IR EAX is not the issue. Remember last time the discrepancy comes from EBX. So we'll look at EBX this time, and there's no discrepancy. There's no discrepancy because when I use the examine command, it shows us it has this content in hexadecimal. When I look at EBX after the instructions execute, it has the same exact bit pattern. Okay, so I think this confirms my suspicion. So now the new question is, what do you think is my suspicion? The breakpoint, very good. Okay, I like that thinking. The breakpoint is changing the instruction. Okay, can anyone guess how breakpoints are implemented?
It's a no-op.
It's not a no-op, it is a special instruction. Okay, so when you set a breakpoint in a program, what GDB is really doing is changing that location to a special instruction. Okay, which causes the processor to intervene and say, okay, we need to stop here. When the processor stops, then it will consult with GDB and say, what was here earlier? Okay, so that you can actually finish executing the instruction when you single step. So when I set a breakpoint on the location, it actually changed the content of memory at that location. Okay, but if that is the case, how come the X command did not see that change? It's only showing up when we actually look at the instruction itself. That's because when we use the X command, it is actually,
Skips the breaks.
No, it restores the content.
Mm-hmm.
One will restore the content first, so that you would not actually see the byte changed by setting a breakpoint.
Okay.
So when I ran this experiment differently, because I did not set a breakpoint in the first 3 instructions, that's why the content did not get changed, and we did not see the discrepancy in this case.
Okay.
Okay, that explains it. I feel much better. But that's the whole thing. I mean, I'm not really sure how many people are getting this, but I do not like questions unanswered. And unlike you, I don't have my own professor to ask anymore. So what do I do? What did I do?
Set up experiment.
Set up an experiment. Come up with a suspicion. Okay. Well, okay. I'm not expecting you guys to come up with that type of thinking, because I have written assemblers, debuggers, and stuff like that before. So I kind of understand the underlying implementation of setting breakpoints, how debuggers work, and stuff like that. So I'm not expecting that from a class like this. Okay, you're maybe about 10 years away from being able to come up with that type of a suspicion. But it's the approach. Okay, it's the approach that is important. Okay, in the absence of someone to ask, like a professor, try to come up with your own solution. Okay. Think about it a little bit and see if you can come up with a solution. All right, so this is all good. This is all good. All right, so now we have implemented or talked about several types of addressing modes. There are more. So let me go to the module page here. So we have talked about assembly language constructs. We talked about memory sections. So basically we have a .data section where you can store your global variables, and we have a .text section where you can store the instructions. Okay, I have not demonstrated .data just yet. Okay, so the next question is, do you think we can change instructions on the fly? In other words, can I pull the rug under myself, so to speak? How do we test it? Okay, that's the next question. How do we test it? How do we know that we can or cannot do that in a program? So let's go ahead and look at this program. Okay, the very same program that we have been playing around with. And we'll go ahead and say, let's do something like this. Let's say we want to move a byte. Okay, this time it's just a single byte. And we'll go ahead and move 0x, I don't know, just give it some random values here. Okay, 5D, okay, for no particular reason, to _start. Okay. All right, so look at this instruction here. Let me turn on the line number so we can focus on line 7 in this case. So on line 7, what is the first operand? What is the type of the first operand? It has a $ in front of it. It is a immediate operand, which means 5D or 01011101 is the actual bit pattern that I am copying to the second operand, the destination. What is the destination operand in this case? It's a direct operand, right? Okay. In other words, _start as an expression is specifying the location where that byte is going to overwrite. Is that okay so far?
Mm-hmm.
So I'm not overwriting the label itself. Okay, you cannot change a label, but you can change the location pointed to by the label. Okay, so I'm going to overwrite a location that is already kind of in the past. I can change it any way I want. It won't crash the program. So when I run this program and it crashes, it can only mean one thing. What is it?
The instructions come back to the start sometime?
I cannot change an instruction.
Oh.
The process, the program itself cannot change its own instructions when it is in the .text section. Okay, that's what I'm testing. I want to find out. Now, if you remember from last time, we talked about the NX bit. Remember the no execute bit? We talked about that. This is actually an experiment to see if the NX bit is actually active. Because if it is active, I should not be able to change the instructions. All right, so let's go ahead and change, reassemble, relink, and this time I'll run it outside of GDB first. It does give me a segmentation fault, which means I cannot change an instruction in the .text section, which makes sense, okay? Because that's what NX is supposed to do. Well, part of what it's supposed to do. All right. So let's see if it will do the same thing when I'm in GDB. Okay, so I just go ahead and run the program at full speed, and it does give me exactly the same thing. And on top of that, okay, now when in the rest of this semester, many of you will write will deal with your homework assignment, and you will encounter segmentation faults. Okay, it's very easy to get into a segmentation fault in assembly language program. When you do get that, don't just give them and go like, my program is not working. Okay, what do you do instead? Do it in GDB first, and find out where the problem is. Okay, because it always tells you something about why you have a segmentation fault. In this case, what is it telling me? What are the 2 lines after program receives signal, segmentation fault, what is it telling me? It's giving me some really useful information. Because of the entire program, let's say I have written a 200-line assembly code program. Do I have to suspect all 200 lines as the immediate cause of the segmentation fault? Or is this already telling me something to focus on?
Focus on 7.
On line 7, okay, very good. So on line 7, can the first operand possibly be the cause of the problem? Is an immediate operand. Can an immediate operand cause a problem? No, because it's just a constant, it's just a bit pattern that is stored as a part of the instruction itself. So if the first operand as an immediate operand cannot be causing the problem, what can it possibly be? The second operand. Okay? The second operand is either specifying a location that I cannot access, or a location is, in this case, that I do not have write permission to. I have read permission to that location because I can run the program, but I do not have write permission to overwrite that portion of the program. In other words, using this particular mode of operation, I cannot write self-modifying code. Has anyone heard of that term, self-modifying code? Okay, in what context?
Just as a theoretical term.
Okay, so for those of you who are interested, you can look up self-modifying code, and Wikipedia probably has a page. Yes, it does. Not surprising. Okay, so we'll just go ahead and read the portions of the first paragraph. Is code that alters its own instructions while it is executing, usually to reduce instruction path length and improve performance, or to reduce otherwise repetitively similar code, and thus simplifying maintenance. Okay, so it had a purpose to exist. Why are we getting out of self-modifying code? In fact, I will not encourage you to write self-modifying code even if it was possible. Why not? How do you debug a program that is self-modifying? You can, but it's extremely difficult, okay? Because it depends on at what point of time you're looking at the program. Because the source code is no longer representing the state of the program anymore. Because the program itself can change its own code. Does that make any sense? Okay? So in a way, our mind is self-modifying because it's constantly changing, and yet it affects how we do things. And yet how we do things continues to go back in feedback and change the way we think. So we are actually prime examples of self-modifying code, but in a good way in most cases. But there are other ways or other applications of self-modifying code. Let me see if I can find that word here. Nope, okay. Protection. There we go. Used as camouflage. Self-modifying code was used to hide copy protection instruction in 1980s, which some of you may not have been born yet. Disk-based program for platforms like IBM PC and Apple II. On an IBM PC, the floppy disk drive access instructions would not appear in the execution program image, but would write into the execution in memory image. So they were using this, Microsoft, to be more specific, was using self-modifying code so that people cannot bypass the copy protection mechanism easily. Because otherwise, people can just load the executable of a program into a debugger. Okay. Now, Microsoft DOS or MS-DOS did not have GDB because it's not GNU-based, but it has its own debugger. Can anyone guess the command of the debugger in Microsoft DOS, MS-DOS?
Debug.
Debug, exactly. And guess what? Debug can do many of the things that we can do with GDB, which means someone can disassemble a program to figure out how the copy protection mechanism works. So what do you do after you figure out how a copy protection mechanism works?
Disable it.
You jump around it, or disable it, right? And by the use of self-modifying code, that task becomes a lot more difficult. Becomes a lot more difficult to pinpoint, where to insert the extra jump instructions so you can bypass the entire copy protection mechanism. If someone was to do that again today, which law is going to be violated? There's a very specific law or agreement that applies to that sort of thing. Any attempt to bypass copy protection is going to be violating which agreement?
Is it the DMCA?
The DMCA, which stands for?
Digital Millennium Copyright
Act.
Act.
Yep, so that's the big thing. I know this is kind of not so related to this class, but it is in a way. DMCA is the Digital Millennium Copyright Act. And if you look up Wikipedia, from here you can see how long this document is, because it's very controversial. Because it doesn't say that you cannot criminally do it, okay? It means you cannot do it, okay? I will give you one example. Let's say you go to, a long time ago, you go to a store, you bought your own DVD, okay? And you say, well, DVDs, they lose the content over time because of scratches and other reasons, right? So you say, oh, I have this software that can back up my DVD, all right? And then you say, well, since I bought the DVD, I bought the right to the content on the DVD, so I should have the right to back it up just in case I lose it. When it turns illegal or criminal is when you distribute the pirated copy of the DVD and you give it to all your friends, right? Okay, you put it onto Google Drive and you send the link to everybody. Okay, that would be criminal. That would be illegal because your friends did not purchase the right to that particular content. But if you use it as a backup and say, okay, in case the DVD is scratched up, I will still be able to watch the movie again, that's okay because you have the right. And even the movie industry recognized that you have the right to make a backup of content that you have bought. Okay, it's not a problem as far as the law of, making a backup is concerned. But the act of making a backup requires you to bypass a copy protection mechanism. So it's illegal. do you see what I mean? Okay, it means, going to a certain location is okay, it's legal, but the way you get there is illegal. Do you see what I mean? Kind of? Okay, yep.
So it's applicable only to the United States or all over the world?
Well, from the big old seal here, you can tell that it's only applicable in the United States.
Okay.
Yep. But for those of you who want to read more about this, you can definitely go to this website, because a lot of application of assembly language programming, or the flip side of this, which is disassembling and trying to figure out how things work, they all point in this general direction of how do I bypass something. So the act of bypassing is illegal already. It's not what you do with the stuff that you copy. It is the act of trying to bypass copy protection that is illegal. Alrighty, I'll be at the lab to answer questions about the homework assignment. I don't think you guys will have a lot of questions, but just in case.